Okay, so we'll continue along this line of soil fertility evaluation, and this is really going to be this next slide set's going to be talking specifically about soil testing in this whole vein of kind of developing fertilizer recommendations. How do we go about this? Before I really dive into it, I want to talk about 4Rs for nutrient management. So 4Rs are something that I could have talked about really the first week because it's a pretty important concept. But now's just as good a time as any to think about what this beast is. So not the most exciting thing in the whole world, but anytime we're talking about fertilizer management or nutrient management or fertilizer recommendations, we can think of these 4Rs. And that's really the right source, the right rate, the right time, and the right place. So the 4Rs are all the rights. Again, not my most favorite marketing or packaging, but it's just what it is, and it's kind of a very universal, widespread idea. So source, of course, deals with types of fertilizer. The actual, is it what is the fertilizer that you're using? What is that source? And then the rate is actually how much you're applying. Timing deals with when it's applied. Is it applied in the fall, at planting, mid-season? Placement is how it's placed. Is it broadcast? Is it banded? Et cetera, et cetera. So um, there used to be an organization, IPNI, and International Plant Nutrition Institute. This was a fertilizer industry kind of scientific branch of the fertilizer industry. Unfortunately, they did a lot of good things, made a lot of materials. You're going to run into some of their materials in the course of your career. Unfortunately they have lost funding and they have essentially been disbanded, and so a lot of that responsibility has been taken up by the Fertilizer Institute. So it's really unclear what that's going to look like, but that's a bit of a digression. But IPNI is widely credited with this concept and this packaging of the 4Rs. So just something to be aware of. Okay. And we've talked about what makes up a standard soil test a little bit, but let's kind of dive into this again. And so when you pull a soil sample and you contact a commercial lab and say, I need, a soil analysis done, and this is, of course, there's lots of different measurements in soil science, but what I'm talking about are the commercial soil testing labs, okay? They're often going to have packages. We've got an S1, an S2, or an S3, or we've got a soil one, or like whatever. But quote unquote a standard package that they offer, and that nearly always includes soil pH, a CEC, that's cation exchange capacity, of course, extractable cations of calcium, magnesium, and potassium, and then extractable phosphorus. So almost every commercial lab is going to offer you that as kind of the fundamental baseline. Their packages may also include things like organic matter percentage, a buffer pH, which we've already talked about, for that liming requirement, and then possibly extractable micronutrients, things like boron, zinc, manganese, et cetera, et cetera. So that's really what's kind of the foundation or the bread and butter for a lot of soil testing. Now note, we've already talked about this, but note that nitrogen, a measurement of nitrogen, typically isn't included, right? So soil nitrogen isn't directly measured many times. Some people say, oh, if you get organic matter, you can have a sense of that, and that is true to some extent, but it's certainly not a really precise value. So soil tests, depending on the lab that you send, we have a really rich infrastructure that is very easy to take for granted, but there's been a lot of public investment over the last 60, 70 years in figuring out how to take soil and find out its ability to supply nutrients to crops, right? And so soil testing is a large industry, and we are very lucky, very fortunate to have a number of really good labs in the state and in the Midwest that can service and are happy to run soils for us. So if you've never submitted a soil sample or looked at a soil test report, they come in different shapes and sizes, but essentially here's a report with 6 soils in it, or different sample IDs. The lab is usually going to give it some kind of internal number. Here's organic matter, here's phosphorus, and potassium, magnesium, pH, etc., etc. So we can go through some of these, and we'll deal with a little bit more of this as we get into it. But what we can see is that these values have an H, L, L, sometimes an M, H. And what does that mean? Or VH, so very high, high, medium, low, or even a very low. And so that's kind of a relative, it's a way for somebody that gets these results to understand, are these values good or are they bad, right? So typically like an M would be, and again this is going to depend on the lab, but an M would be medium, that's kind of optimal, or high, you know, depending on how they code these. Differs by lab and depends on, you know, who's actually running that result. And you might say, I'm growing potatoes, and that might be very, or I'm growing, you know, I'm planting an apple orchard, and that, and if you tell the lab that, these values might be coded very differently depending on the, you know, on the nutrient needs of that crop. So it's important to understand, of course, that we can get a number, but knowing what that number means and how it relates to what we're trying to achieve can vary widely depending on the crop and on the, you know, the interpretation of that. So, you know, here's another. This is another. So this is ENR Labs out of Fort Wayne, Michigan, a very large lab that services a lot of Northwest Ohio. Michigan State University has their own public lab. It's not particularly a large lab, but they, you know, they run, and they've got this, instead of a high, medium, and very high or low, they've got below optimum, optimum, and above optimum. Okay, so again, these are, and here you see recommendations for a home garden, and so if those recommendations for, you know, a wheat field, it might be different, and it would be different actually. Okay. Just showing you some more examples of what this is. So, you know, this is a good example of, you see the result. So here's kind of like the absolute number based on the different nutrients. Calcium, magnesium, potassium saturation, we talked about this already, right, with the CEC section. Here's the unit of measurement, either a percent or an M3, a Malic 3 part per million. And then here is, so this is, these two columns are really like the values that you get that are absolute in some ways. But then when we put this optimum column, and that's basically telling you what your soil test values should be. You can see for organic matter there is no optimum because it depends on soil type. For pH, we say 6. They're saying 6.2 to 7. For phosphorus, 44 to 71, etc., etc. So part of this, what we need to understand is we can generate soil values, but when we go to interpret them, if they're high, if they're good, if they're optimal, if they're too low, that's like a whole nother step of interpretation, right? So again, where do these numbers come from? Where do these optimal ranges come from? How are they developed? Why is this green and this one's red and this one's yellow, et cetera, et cetera? So we're not going to get into all this, but it's just important to recognize that, you know, a value of 12 part per million sulfur, Malic 3 sulfur, might be optimal for, or below optimal for one crop, but it might be above optimal or, you know, whatever for another one. So Where do they come from? Where are they developed? How do we actually get soil test numbers and provide interpretation for that? Okay, so there's a mantra in soil fertility, and it's this idea of correlation, calibration, recommendation. So these are 3 steps that occur in order of actually developing a fertilizer recommendation. Okay, so again, correlation, calibration, recommendation. So let's talk about these. So the first one's correlation, which is determining which measurements are related to crop response. Okay, so here we've got something like plant uptake versus soil test extractable P. So we can see that as soil test P increases, maybe our plant uptake increases. But if we look at these 2 different extractants, there's a lot more variability with extractant 2 than with extractant 1. So maybe, we do this work and we say, oh, well, extractant 1 actually is performing better here, okay? And then we can think of taking some index of availability. So again, here's a soil test index. Maybe it's extractable phosphorus. And then we can see over time, maybe we run, some various experiments here, 1 through 4, and we see maybe this is like in a greenhouse or whatever, and we can see that it's somewhere above 50 that no matter how much phosphorus we apply, we don't get any response. But when it goes below maybe 50 or even 30, we start to see differences that happen, okay? So this helps kind of us actually correlate what things are. So the second step, which can blend, of course, the correlation and calibration work can blend together, but calibration is the second step. And here we're actually trying to determine the crop nutrient requirement at different soil test levels. So imagine we have different soil tests and we fertilize at multiple different rates. Okay, we do this across a bunch of different soils and whatnot. And we start to see a convergence happen when we apply, say, 100 pounds of phosphorus, or maybe it's 80 or whatever, there's no additional response that happens. But if we only apply 20 or 30, we can still see some increased yield, okay? We're going to talk about this relative yield here in a second. So then the final step is developing that recommendation. And this is kind of where we have to bring in a number of things, like just a practical view of how easy it is going to be to manage this information. How will the farmers interpret it? How will they actually use that information? So recommendations are often not perfectly scientific. That is, they're often not exact, but there's an element of just kind of ease that are built in. So again, there's these trade-offs between how much, how practical can it be for a farmer versus are we going to provide recommendations? Like, an easy example is like providing recommendations based in saying you should apply 62.45 pounds of phosphorus per acre, for example. Well, a 0.45 of a pound on an acre basis is, a farmer is never going to be able to measure that, right? And so because our fertilizer applicators aren't that precise, and so maybe instead of 60, whatever the number I just said, 62 something, maybe you're just going to round it up to 65 and make it a nice even number, or maybe down to 60 and make it an even number. So again, this is where this kind of human interpretation comes in and just helps make that recommendation easy to remember, easy to implement for a grower. Okay, so calibrating soil tests with plant response or crop response. Again, showing similar things. This is data from Iowa, Antonio Mallarino out of Iowa State. Here's soil test P. This is corn and soybean. And then here's relative grain yield. So any value less than 100 means that we're actually losing yield when we're at 100. Or here is, ladies and gentlemen, here's the dark reality of soil fertility. And it's that it's really messy, right? And you look at this, and I'll ask you, where does this actually break, where we can actually say you should apply fertilizer or you don't have to? Well, of course, it's not very clear cut exactly where that point is. And so again, this is this kind of element of when you're developing a recommendation, trying to be conservative. So you want to ensure that a grower or whoever might, not be under applying, but we don't want to be super conservative, and so everyone's going to consistently be applying more than they need. LP, QP, and XP. So these are three different types of curves that we fit: a linear plateau, a quadratic plateau, or an exponential curve. And depending on that curve, we can get these idea of different critical levels. Okay, so this is a new term, and we'll talk a little bit more about this later, but this idea of a critical level being this magic soil test value of when you should apply or you shouldn't apply, or whether you're going to likely see a crop response to fertilizer or where you're not. Okay, so we can see in this data set, at least for corn, the LP, the QP, and the XP, the linear and quadratic plateau and the exponential, produce very different critical levels, right? So 15, 21, and 27, almost a twofold range here. Now we can look at the response or the fit of that curve and make inferences based on which one's better. But the reality is that this is very common to find in soil fertility, and so there's some kind of fudging or just best guessing, and we need to recognize that when we find a soil test value and say our critical level is 15 or it's 20 or it's 30, it's not a magic number that's going to be perfectly consistent every single time. Okay. This idea of relative yield, we use this to normalize differences in grain from year to year, or whatever, yield from year to year. So this doesn't have to apply, of course, to field crops, but it's going to drive yields regardless of the crop. Some years are good, some years are bad, and so this calculation of relative grain yield on this axis is the yield of the unfertilized divided by the fertilized times 100. So that essentially normalizes everything, puts it on a 100% scale. If it's less than 100, we're seeing yield loss. It can actually, as you can see, be greater than 100. These points up here show that fertilization actually, if the plots that were not fertilized yielded more than the plots that were fertilized. And we infer then that that's kind of random noise. It means that the plots were not fertilizer limited, whatever that nutrient we're applying. Okay, so again, these kind of basic shapes to determine yield response. So there's a linear plateau, an exponential, a quadratic, sometimes a quadratic plateau, and we will use R-squareds or AICs, or just looking at the data, kind of a subjective interpretation of that to kind of determine the best model fit. So these are kind of typically how this is done, and it's why we often get this talked about this a number of times, this generalized relationship of yield loss or productivity declines at low, say, soil testing level or plant nutrient concentration, and as that increases, those start to plateau and become non-significant over time. Okay. So developing plant responses, we can do this in the lab or the greenhouse. These are simple, rapid, controlled environments. But more commonly, we want to do these in the field to make them much more realistic. Greenhouse experiments are often really difficult to extrapolate to the real world, okay? And so for field trials, we can think of either large strip trials or small plot research trials. So greenhouse trials where we might, this is, I can assure you, this picture is from how long ago, but whatever the nutrient we're applying at 1.5, 2.5, all the way to 5, and you can see it's clearly this soil and this plant is responding to whatever that nutrient might be, right? So we can do this and get some idea of levels, but again, because of these pot experiments, unless the crop that you're growing is a potted plant, if it's, then this makes perfect sense. But if it's not, if you're growing in the field, then you're going to often get very different results. So small plot research, university scientists like to do this, but farmers often balk at this because they do not like, well, there's a number of reasons, but as university scientists, we typically like these because it controls the amount of variability that we encounter in any given field. It allows us to do multiple treatments instead of just maybe 1, 2, or 3 treatments. We can do, say, 10 different treatments and get a lot more information. We'll do this typically with a randomized complete block design, have different treatments and different replicates or blocks that we'll call. Growers, we take the approach that we like both pieces of information, but farmers are often much more likely to believe research that comes from large strip trials, and especially comes either from their farm or from a neighbor's farm or from a farm, in their county, someplace close or local, instead of some faraway place in Worcester or whatever that where trials were ran. So, anyways, there's a whole social dimension to that we could get into, but suffice it to say that there's a lot of small plot research that happens at university farms, and we can take this if we've got equipment. We do this all the time. We can take equipment and actually implement small plots on a grower's farm, right? There's no problem with that. It's just that we need typically specialized equipment that are, small planters, small combines, et cetera, but this is commonly done. So the lines can get blurred, okay? And then finally is this idea of large strip trials where, we're using quote-unquote normal-sized field equipment and doing a small number of like treatment 1, like versus control. Phosphorus fertilized strip versus a non-fertilized strip or what have you. The problem with this is that these are typically much larger, and as our field site, our actual field experiment, the area of that increases, from a probability perspective, we're going to increase field variability. Okay, so as the area increases, the variability is going to increase as well. Very commonly, there's very few instances that's not true. So here, we've got 2 different treatments and then 2 different soil conditions, or maybe 3 different soil conditions. And this can really introduce a lot of noise, a lot of variability, and it might really compromise the experiment. And this is why a lot of people don't like to do this, okay? So anyways, just some trade-offs. There's always trade-offs in life, and here's one trade-off between small plots, which give you greater control and less variability, to large plots, which you can do and have farmers implement. They see the results on their farm with large strip trials. You're going to have a much greater chance of encouraging them to, practice or adopt whatever practice that you might be proposing. So, all right, I'm going to end there. We talked about soil sampling, the logistics of that, and with this we're talking, we just finished talking about how we actually go about developing a fertilizer recommendation and the soil sampling piece to that. The next part, we're going to get into some more nitty-gritty about updating the tri-state fertilizer recommendation. So I'll talk about that next.